Today we are looking at forces. That's what we're overall looking at, was the idea of forces. Now, forces are anything that's going to end up acting on an object, and they have got loads of different effects on different objects. So the effects that a force can have the first thing it could do is it could change the shape of an object. So that's the first thing that a force could do. So if we take, for example, this ball, okay, you can see it's got a particular shape. If I apply a force to it, would help if I applied the force properly. So if we take that and we apply the force, you can see it's changed its shape, okay, nice and easy. It's changing its shape, and all I'm doing is applying a force. So when I apply the force, it's going to end up changing shape, and when I release the force, it changes back. So it's pretty straightforward, straight and obvious. Okay, so that's the first thing that it might do. The second thing is if it's stationary, it can move it. Okay, so if that ball was dead still, if I apply a force, it's going to start to move. Okay, that's the second thing it could do. You could also have the idea that if it was already moving, we could end up speeding that object up. So if I applied a force to something that was already moving, it might speed up. Okay, think of a car that's at 20 or 30 miles an hour. If it was already moving and we applied more force, it's going to speed up. We could also have the idea that something that's already moving slowing down. Now that means that the force we're applying is acting in the opposite direction, and it's stopping it's kind of counteracting the force that it has moving it forward and pushing against it to slow it down. Okay, so that's what's happening. Or we could have already moving and stopping. Okay, so that's the other option it has, that it's already moving and so much force is applied to it that eventually it stops. Pretty straightforward. The last thing that it could do is if it's already moving, we can make it change direction. Now technically, that might not necessarily speed it up. It might stay at the same speed. It might speed up. It might slow down. It doesn't really matter too much. But if we're changing its direction, what it means is we're changing its velocity. So technically, it's accelerating, because a change in velocity means that it's speed in a given direction. And let's say initially I was moving this way and then suddenly I'm going that way. My speed is now going this way, which means I've changed direction, I've changed velocity, and acceleration is the change in your velocity over time. That's kind of what it works as. So that's why we would say, a force is applied to it. It's after changing direction and we've changed its velocity. So that's the different ways that a force can impact an object. We could start by changing its shape or size, speed it up, get it moving, slow it down, make it stationary, or change its direction. Any questions so far? Can you change your face too? Technically, this sounds really weird, but if you ever watch someone being punched in the face in slow motion, when it's hit, their face will all move around because the force is applied to it, and your face technically jiggles to dissipate the force all over. So in a weird way, and I know it was a weird question, but yeah, you technically can. I'm on top lives. I'll take it. Look at that. TikTok knows. I really appreciate your teaching the platform. Oh, look, I'm just doing my best. I'm trying to do what I can. I have a question. How big is the moon? Huge. Officially, that's humongous. That's the one you're getting. No questions from me. Wicked. What is resonance? Oh God, off the top of my head, I can't remember. Can you do circular motion? Actually, since we are talking a bit about that, we could discuss what circular motion is. Because if we think about circular motion, and this is me going a little bit off topic, but it's related, and this would bring in Newton's third law a little bit later on as well. If we think about circular motion, we'll take something like the moon, because we were talking about change in direction. So if this was the Earth, and we have the moon, okay, we know that the moon is kind of within our gravitational field, so it's going to be drawn towards Earth, but then it's also moving as well, so it's technically trying to stay away from us by moving. It's got what we call a velocity, so it's going to have let's say a velocity in this given direction, okay? So let's say that's the moon's initial velocity, but because it's got that force attracting it towards Earth is pulling it in, it's going to cause it to rotate around in a circular pattern, okay? So because it's going to end up rotating, it's going to end up swinging this way. So you're going to end up changing its velocity from this direction to this direction. And then let's say once it reaches here, it's going to end up changing its velocity again. So it's over here. And again, that's all because it's still drawn in towards the Earth. Gets over here, still drawn in by the Earth. Gets over there. So it's constantly changing its velocity. That's the key, is that you're going to end up always moving it around in a circle. That's just how it works. And that's because it's got that equal and opposite force drawing it in, gravity, essentially pulling it around in that circle, okay? Even though its velocity is changing all the time. Remember, we were saying velocity is speed in a given direction. So its speed is going to be constant. So the moon is going to have that same speed. That's what's preventing it essentially from being pulled so far into Earth that we have a collision. But because it's changing its direction every time, its velocity is increasing in that direction every time. And when we look at acceleration, that's what we're saying is happening. Acceleration is your change in velocity over a given time period. So because we're changing our velocity constantly, weirdly, the moon is technically accelerating constantly, but it's not accelerating the way that we think of acceleration. I know that's probably a little bit tricky, but the easier way to imagine it is that if you had like a ball on a piece of rope, okay, so if you've got anything that's like attached to a piece of rope and you started swinging around in a circle, you'll start to see that as you speed up, it starts to get pulled further and further out. The reason why is because it's gaining more speed and its velocity, it wants to shoot off in a straight line. But because it has more speed, that's fine, and you've got that force between you and that object and it's pivoting around you, okay? You're like the fulcrum. It's going to end up going around in a circular pattern. I hope that's kind of answered your question about circular motion. So can I do the photoelectric effect? I can't even remember that at the moment. I can do it, but I'd have to like have it reasonably prepared beforehand. Very funny, whoever that person is. Have I heard of that scientist? Yeah, very funny. Is the Earth round or flat? It is round. Well, technically, when we look at it, it's not even perfectly round, but weirdly, based on the size of it, it's almost the roundest object that we have within our universe, because you have to look at the surface itself. But yeah, if we're considering that whole round Earth versus flat Earth, it's round. It's most certainly round. Someone said, is it possible that the moon's the moon's velocity could change? As far as I'm aware, it's pretty constant. That's why it stays within our orbital. And it's the same when we look at like all of the different planets that are orbiting around the sun. We've got that constant speed. So even though our velocity is changing, the speed around it is constant. Where you look at stuff that doesn't is, I think if I remember this rightly, and I could be wrong, but I'm almost certain I'm right, is when you look at like comets and asteroids, because they don't have the same kind of orbit. The only time it generally changes, and you might have heard of people talking about this with NASA and with like space rockets and stuff like that, is about slingshotting stuff around it, and that's using the idea of gravity to pull you in close to to something that has a strong gravity like Jupiter, and then being flung out the opposite end so that you gain more momentum. So that's kind of part and parcel to it. There's a lot going on there that I can't fully get into because I'd end up losing a lot of people. Can you explain the Doppler effect? I'll do it quickly because that only takes 2 minutes, and then I need to get back to talking about forces. So the Doppler effect, let's say, we'll put me here. Okay, there's me, side of a road, and driving on the road. Wicked little car. We'll give her a spoiler as well. Let's say my sister is driving a car. Steering wheel. There she is, delighted with life. Hair everywhere. She's delighted. Okay. Oh, we'll give her. Well, she's smiling. There we go. Let's say she's driving along the road. Okay, and she beeps her horn on the car. So she's beeping the horn on the car. So they're going to produce some sound waves. Now, sound waves, they work through longitudinal waves. So that's like you've got all these particles, and when they bump into each other, it transfers the energy across. So the front of that car is going to be producing sound waves. Okay. So let's say those sound waves moving towards me. Now, because she's pushing or she's driving forward, those sound waves get compressed. So they get compressed, they're pretty close. Okay, there's not a whole lot of space between them. They get compressed, okay, and that's why we hear a certain tone as we come closer. It's because on the way to us, when they're moving towards us, okay, those sound waves, as they move towards us, they're compressed. So that's why we hear that initial sound as we drive. So as she's moving along, she's going, and then as she gets past me, it changes. So it goes, that change is because the sound waves are no longer compressed. Because it's gone beyond us and they're moving away, they end up being more spaced out. So that's what the Doppler effect is. So she drives past, she's at this stage over here. I don't know what happened to her car, but it's after changing its shape as well. She's going to drive past. So as she's gone past, those sound waves, they end up spacing out, so they're less compressed. So as they're moving away, they're less compressed. And that's what's happening with the Doppler effect, is that we are just changing how compressed those sound waves are. Now, the Doppler effect works with loads of other things as well. So you could think of in space, we look at redshift and blue shift. What is it? Redshift is looking at the objects moving away from us, and that produces red light because that's the longer wavelength. Whereas if it's moving towards us, the wavelengths would be more compressed, and that's blue light. So that's where we come with this red shift and blue shift thing, but there's loads in there. But that's what we're looking at essentially with the Doppler effect, is the compression of waves. Okay, I'm going to move on because that's not what I was supposed to be teaching today. But let's talk about how forces can be applied, or what we see happening when we're actually doing these things with forces. So we can apply a force in a couple of different ways. We could have a push, a pull, or a twist. Okay, there are three kind of categories of forces that we're going to be dealing with, where we see something either being physically pushed, physically pulled, or we're twisting. If we think of an example for each, twist is pretty straightforward. You just have to think of a lid. So if we look at the lid of this bottle, okay, let's say if I'm applying a twist, I'm technically pushing on one side and pulling on the other. It's almost a combination of the two at the same time, and that is going to end up causing a twist. Okay, when we're looking at like how cars move, we're actually looking at how the wheel itself is twisting around in a circle, and we end up dealing with something called torques. Some of you will have like dealt with that before. So that's what a twist is. A pull is pretty straightforward. You can think of something like if you had a box and there was a rope attached to it on top. So you had a rope attached. That would be your pull. Okay. A rope pulling. Rope pulling a box. A push, something that happened regularly to me when I was a bit younger. You could think of a car being broken down. My cars are brutal. I need to get better at drawing those. And you can imagine someone at the back just pushing the car. What in the name of God is that? That was the worst stick man ever. There we go. Put a little sad face. Okay? So, push. You're physically moving the object forward, whether that's with a person or a machine or whatever it is. Pull, you're moving it towards you that way. And twist is a combination of both. Questions? Questions? Okay, hold on. If the universe expands faster, does that mean that gravity can also pull apart rather than together? Oh, that's a good question. I don't know. Float and sink? What's the float and sink about? Oh my God, we got all the trolls in today. I love it. We got all the trolls. Anatomy of a female. Well, I'm about to say, if you don't know that yourself, there's not a lot of hope for you, is there? My God, what are these comments today? All of the trolls in. I love it. General relativity. Do you know what? Ask me that question over my Instagram. I'll put up a comment later on because I'll give you a lot more detail on it there. Physics or biology? Mostly chemistry, to be honest. Biochem and phys. I kind of do a bit of everything, but it just depends on the day. Can you explain how tension affects the force applied to an object? Do you know what? I'm going to go into tension a little bit in a minute as well. I retaliate to everyone. Life of a star. Lads, the amount of questions, I'm actually surprised. I'm going to have to put up a question, but I didn't think I'd need a question box up on my Instagram today, but we'll get into it later on. I'll move on with this one again, and I'll put up that question box. I really am surprised at the extra amount of questions I have. So, there are two main types, or two main groups of forces. So we've got contact and non-contact forces. Okay, pretty straightforward idea of how to identify the differences between the two of them. Contact, you're going to have objects touching. And then for the non-contact, the forces won't be touching it. So let's talk about the different kind of ones we have. So we've got reaction. Reaction I spoke about earlier. Reaction is when you have two surfaces touching and they're acting in equal and opposite directions. So reaction forces might be something like a box on a table. You have a box on a table. The box is acting downwards on the table. Then the table is also acting upwards on the box. Okay, so this is where Newton's third law applies, where we're talking about an equal and opposite force. Because if they weren't equal, then the box would just slam straight through that table. So there has to be a force acting up against it. So that's what where we bring in Newton's third law. Okay, so that would be reaction. The second one that we have is tension. And someone was asking about tension a while ago. So similar enough idea here. You might have a box. And you're going to have some sort of a rope or a cable pulling it up. So the box is acting downwards, but the cable is acting upwards. So again, we have these opposite forces, and depending on how much tension there is, so you could have a tension where, let's say, it's a gradual build-up, and you tend to see that the object then moves in the direction of the tension once its force is greater than the force of, let's say, gravity acting downwards, because that tends to be a big one we deal with. But if you were to pull it too fast, so you apply too much force too quickly, and I don't know if this is answering the question you're kind of asking, but if you apply too much force too quickly, then it's going to end up like potentially breaking your object. You see it all the time when like you get two people trying to tow like a truck or a car or whatever it is. The person doesn't build up the tension slowly in the rope, and then because they rip it, they're going to end up like pulling someone's front bumper off. Whereas if you slowly build up the tension, then it starts to move it in that direction as well. So that's what tension is. The next one we have is friction. Okay, so friction is pretty straightforward. You have a surface, you have an object, and you might be trying to move the object in this direction, and then friction is when the second surface is going to be acting in the opposite direction. If you want to apply this right now in front of you, take your two hands, put them together and rub. Okay, you're going to feel friction acting and releasing the energy as a different form. You're going to end up feeling heat, and the faster you move it, the more heat it generates. So that's going to be a sign of that you've got friction between the two surfaces. Now we can then also talk about how you reduce the effect of friction. So you might apply something like water or oil or something that's going to act as a lubricant in between your two surfaces, and that's how you reduce energy loss by friction. Something I like watching a lot now more recently for some reason is something like Formula 1, where a big thing for them is trying to recoup energy and prevent energy loss. And the big thing for them is making sure they've got the right lubricant in their engines so that when those surfaces are rubbing off each other, they're not losing a lot of energy, and it makes everything more efficient. So that's something that's massively important for anything that's got like a machine or mechanical process, is reducing the amount of energy lost through friction. So again, if you want to try it, literally rub your hands as fast as you can together and you'll feel the friction between your two hands. Coincidence, I just joined. F1. Oh, look at that. Ferrari lad's in. Look at that. Perfect timing for you, my friend. Perfect timing. Any other questions? Yeah, Ferrari lads, big fan. I'm a big fan of F1 recently. Loving the season so far. I mean, first two races have been incredible. Okay, so that is the third one. And again, other examples that you'll see of it might be if you have a car on a road, all four tyres are touching the surface, so you're actually going to have friction between the tyre and the road. That's why it's really important to have good tyres at all time with lots of grip, because it's going to keep you glued to the floor essentially. And the last one that we have for this is it's very similar to friction, but it's just slightly more unique. It's air resistance. Now, a lot of people are going to be like, how is air resistance considered a contact force? Like, you can't see air. You might not be able to see it, but there are loads of particles inside in the air. And if you've ever been like running or out in the wind, like you can feel that force coming towards you. That's air resistance. So if you can imagine like flying in an airplane or falling out of the sky in a skydive, then you're going to be feeling the force of those particles at you all the time. That's air resistance. It's you coming into contact with the particles around you. I don't really know how I can draw this properly, but if you can imagine that there's all these particles in the air, and you just have an object bumping into them, that's essentially what's happening. You've got all of the air particles, your oxygen, your nitrogen, whatever you're dealing with inside in the air, and they're essentially hitting off that object, slowing it down technically. That's what air resistance is. Now, it's not a massive force, but it is still a force that's going to be... it's still a force that's going to be applied to your object as it's moving down. Yes, gravity is probably going to be the more important force there, which we'll talk about in a second, but it's still a force acting in the opposite direction. Okay, any questions about contact... I'll move over that side. Anyone have any questions about contact forces? Do you do maths or just science? Just science. There's other maths teachers on here who do it on other days of the week as well. Does tension combat and weaken the force applied? It depends. So like if we were thinking of tension in the sense of like you've got gravity acting on this box downwards, okay? So that's going to be your force acting down. The tension across it on the way up would counteract it and let's say keep an object in suspension in the air. So it just depends on the amount of force that you have for that tension pulling it up. Is electrostatic a contact force? It's not. I'm actually going to put that over on the other side in a second. Principle of conservation of momentum. We talk about particles bumping into each other. Is that what we're dealing with there? So anyway, let's talk about the non-contact forces. So we have got 3 different ones. First one is nice and easy, something that we're used to seeing is magnetic. Okay, so pretty straightforward. You're going to have maybe 2 magnets. If it's north and south here and it's north and south here, that's going to be drawing them towards each other. Okay, so that'd be straightforward. But if it was the opposite way around where we had 2 norths moving towards, or 2 norths facing each other, sorry, then you're going to see them moving away from each other. They're going to actually want to go the opposite way. So they'll want to pull away and that's going to want to pull away as well. So that's what a magnetic force is. They're not technically in contact, but the opposite poles will attract and the same will repel. So that's the key with magnetic. Very similar idea when we look at electrostatic, our second one. Let me make that smaller so that I have more space. So when we look at electrostatic, very similar idea to our magnetic. We have our positive particle or positive charge, probably something like a proton inside in the middle of a nucleus. And you might have an electron that's going to be a negative charge. They're going to be attracted towards each other. Okay, if we have 2 positives, they'll repel. If we have 2 negatives, they repel. But if we've got opposite charges, they're going to attract. Okay, last one then for our non-contact is gravitational. Okay, we're all used to seeing gravitational. It's the idea that a force pulls you towards the center of the earth. Okay, so it's dropping. If you have an object in the air, it's just going to fall. Depending on what your planet is, it changes, because actually what we don't really talk about too much when it comes to the force of gravity is that it all depends on the mass of the object. So bigger objects with bigger masses will end up essentially having a greater amount of gravity towards them. That's why small planets don't tend to have as much gravity. We kind of need to change how we think or view gravity. The way you should be picturing it is like a trampoline. Okay, so if you can picture a trampoline, I don't really have room for it, but if you can picture a trampoline where there's nothing on it, okay, so you've just got your trampoline and then you decide you're going to put a couple of marbles on it, right? If you were to try and push them around, they'll move around the trampoline relatively easy. Now, if you took a slightly heavy object and you place it into the middle of the trampoline itself is going to like bow down, so you're going to end up seeing this push downwards. Now, the marbles that you had in there will end up going straight down towards it. That's the pull towards the big mass in the middle. That's what's happening when we deal with gravity. We're looking at a big object with a lot of mass pulling other things that are smaller than it towards it. Now, if you took, and this is, we're actually bringing back our circular motion again, if you had that big object pushing down the middle of the trampoline and you took one marble from the edge and you pushed it around, so you're actually not aiming towards the object in the middle, you're aiming around it. It's going to go around in a circle. Now, if it was able to maintain the same speed, it would go around that object forever and ever. But it's going to have friction slowing it down, so that's going to mean it's going to reduce speed, and that's why we see it spiraling towards the middle. If somehow we were able to maintain the speed, it would stay going in that circular pattern the whole time. Okay? Now, if you took 2 objects and you put them in the middle of your trampoline, you put space them out so there's a gap in between both of them, and you pushed your marble in, it could technically do a figure of 8 around the 2 of them based on the pull that both of them have. So it kind of slingshots it around enough that they create this figure of 8. It's pretty cool to see, but that's what we do with planets. Escape velocity. It's essentially we're looking for the velocity. That's what we're talking about with the objects moving, yeah. What day is the discussion of chem? So at the moment I'm doing a rotation on Wednesdays between biochem and phys. I will probably end up doing chemistry next week, so you will be back there again. And depending, I'll see what June and July is like. I might do, 3 days a week, but realistically, I think June and July could be busy for me, so I'll stick with the one day for sure. Okay, I'll do the endothermic and exothermic one kind of quickly. I've seen that question there, so we might as well do that. And it only takes 2 seconds. It's chemistry, not really physics, but we'll do it. So, endothermic, I'll write in blue. And exo. So endothermic, we have got energy absorbed from our surroundings, and that makes our surroundings feel cold. You could largely argue that your ex-girlfriend is endothermic because when you're around her, you feel her chill. Okay, exothermic is energy released. And that makes the surroundings feel warm. Or hotter. And that's like hanging out with your buddies because it makes you feel warm when you're around them. You enjoy their company. So we all love exothermic reactions. We all hate endothermic. So exothermic good, endothermic bad. Endothermic ex-girlfriend makes you feel cold. Exothermic, your buddies make you feel warm. Okay? Yeah, and then we'll go for the more obvious ones as well. Endo means that it's entering. Okay? Energy is entering, whereas exo means energy is exiting. So think EX for exit and EN for entering, okay? Any other questions? Any other questions, and we'll move on again because I want to get into our force diagrams a little bit. Anything else? Where are we in terms of time? We're flying it. Wicked. Any other question before I move on? Yes? No? Maybe? I don't know. Can you repeat the question? Delta H. Delta H stands for the change in energy. So, like, if we were looking at the delta H of an object, because I know you're probably thinking exo and endothermic reactions here. So let's say we have our energy profile. So that's what I'm going to assume you're looking for. So this is energy on the y-axis. Well, I've gone off of forces very quickly. Okay, so you can see here, let's say, or are we going temperature? No, we're going energy. So if we were looking at energy there, you could say that's our starting point. We're going to be ending up here. So this would be what your delta H would be that change from that point up to that. Okay, so that would be your delta H. Okay, this whole thing, this is what we call activation energy. Shortcutted as EA. Okay, and this here will be the energy released. Whereas this here is the energy first absorbed. Because to start the reaction, you have to kind of put in some energy, otherwise you don't kind of get it going. If you think about a fire, so like if you were like trying to start a fire at home for the winter, you have to like light a match and put it onto whatever like timber or coal or whatever you're lighting. So that's the activation energy to start it off. But once it starts off, it then starts to release energy. Now, if the energy that's released is less than the energy you put in, that's what we call an endothermic reaction. But if this was way down here and we gave out loads of energy, that's what we call an exothermic reaction, because it gave out more than you put in. So I hope that's kind of what helps. But delta H is that change from the start to the end. Okay? Oh, go away, teacher. Bye. Bye, Felicia. So bond breaking, yeah, I really should do a full lesson on the exo and the endo part, but I think I want to get back and finish off the forces stuff. I have a physics exam tomorrow. I need help. Well, ask me your question, Sarah. Are there any instances where energy release is equal to energy absorbed? Yeah. So if you saw any point where there were like, let's say the energy for bond breaking was equal to the energy for bond making, then yeah, there probably is. But now, realistically, it's only going to be like a couple of joules of energy either side. In terms of energy, it's going to be so minute you might not actually see any change in the energy, the temperature. But there might be one or two out there, but I'm not going to lie, I don't know which ones they are. Normally, I'm just calculating it as I go along and go, oh yeah, that's an endo, that's an exo. TWT stands for Teach with Tig. It sounds like a really weird one, but that's my other profile on here as well. The first one I started where I used to teach and make jokes about school and stuff like that. So like TWT was based off of Teach with Tig, and then I was like, do you know what? I'm just going to have one channel for teaching and one channel for like making jokes about school life and what it's like as being a teacher. So I've got two different channels. That's what TWT stands for, Teach with Tig. Wouldn't that mean the equilibrium stays the same? If we were looking at chemical equilibrium, if we were looking at that essentially you would be thinking that equilibrium stays the same. But it depends as well. If we're talking about dynamic equilibrium, you're looking at something slightly different, because that's about the rate of the forward reaction equaling the rate of the reverse reaction. So it just depends on what your definition of equilibrium is linked to. Plants and biology I'll do in another week. Do you teach in school? I do, but Wednesdays is kind of like an early finish for me, so I try and come on and do a live lesson here if I can too. Can I go? Someone keeps asking me, can I go over plants and biology? I will another time, but not today. What grade is this for? It's like GCSE level, so if you're like leaving cert physics, there's going to be parts of it for you. To be honest, it's kind of suitable for everyone though. Right, let's talk about force diagrams, because I want to get back to, I need to use this on YouTube, so I want to make sure it's sticking with what I'm going to be putting on the title. So in terms of forces, we can have what we call force diagrams, and we can also look at vector diagrams as well, because vectors are essentially forces in your given direction. So let's take something straightforward, and we'll go back to our car again. So we have a car. Which way do I want to go on? Okay. Got a spoiler, so this is the front now. Okay, so that's my car. It's moving forward with a force of 2,000 newtons. Okay, and it's got resistance. It's going to have friction acting against it, and it's going to be 1,000 newtons. Okay, this is kind of your bog standard kind of question that you might see when it comes to force diagrams. So I'm not going to go into huge details and practice loads of them with you, but I will give you some things that you need to keep an eye on. The first thing that you're going to have to figure out is what's what we call the resultant force. So the resultant force is like the net force. Basically, when we try and get rid of all the different forces that are involved in this question, what's left over? So we can see we've got 2,000 acting to the left, we've got 1,000 acting to the right. Could anyone tell me what would our resultant force be in this situation? 2,000 newtons left, 1,000 newtons right. What's our resultant force? What do we reckon? What's the resultant force in this question? Okay, someone said 1,000 newtons, and you're off to the right start, but let's say 2,000 minus 1,000 is equal to 1,000. But we are forgetting something. We are forgetting something really important. We can't just say 1,000 newtons. We also have to state the direction. So which direction? There we go. First person to nail it. Is that Joshua? Nail it, Joshua. 1,000 newtons to the left. Or you can say west if you want to be really fancy. Okay, so that's how you would judge it. Now, based on the fact that this car, this is the front of the car, what other word could we use to describe its movement if we see that those forces are balanced, or sorry, that force is 1,000 to the left? What word could we use to describe it? If we have a net force in a direction and it's the front of the car. Beautiful. Someone's like, acceleration? It is. So this, when we have more force moving this way, okay, and it's the front of the car, we're going to say it's accelerating, okay? So that's accelerating overall. But let's change it a little piece. Let's say now, oh, sorry, and the other thing I meant to mention there as well, the other way that you'd know that these forces aren't balanced is the size of the arrows. So you always have to take into account the size of the arrows. Okay, so if it's a smaller force, it's going to have a smaller arrow. If it's a bigger force, it's going to have a bigger arrow. So the length of it is massively important. But I'm not too bothered about it right now, especially because I'm half rushing it. But let's say we end up in a situation where we have something like this. Okay, we've got 2,000 newtons going to the left, and we have 2,000 newtons going to the right. What do we reckon? Is it, what's our resultant force going to be, or how could we describe it? How could we describe this situation, or what's our resultant force? Balanced, no acceleration. Good, I'll take that. There's another words we could use. Oh, see, now this is where I'm going to get into an interesting one. So someone said at rest. So in this situation, we've got 1,000 newtons moving forward and 2,000 newtons moving to the left. And we've got 2,000 newtons going backwards. So that would be, let's say we're driving forward and then we have friction acting the opposite direction. So our resultant force is 0 newtons. Okay? Now, I saw someone mention at rest. I've seen a lot of people say the word balanced. And balance is probably more accurate to it because yes, they are balanced, but it's what we call constant speed. Okay? It's not accelerating, it's not speeding up, it's not slowing down, so it's that constant speed. We wouldn't say it's at rest, and that is the kind of common mistake that I tend to see with this from students. You don't say it's at rest because we definitely have a force of it moving forward and definitely a force of it moving backwards. The change where we would see it at rest is if you saw this. If you had 0 newtons on both sides, then there's no force acting forward and there's no force acting backwards. So then you would describe it at rest. But because we definitely have forces involved, then we can say it's going to be constant speed. Okay? Now let's say we changed it again and this became 3,000. I don't think we're going to have to do it as a question, but you'll see it here. If it was 3,000, it would end up being minus 1,000. So you're going to have 1,000 newtons backwards to the right. And that's where you would see deceleration, okay? So you're going to end up seeing it slowing down. And that's what's happening when we're actually physically slowing down our car. Any questions? Any questions, anyone? Force connected with speed. So speed is your, like, the amount of distance you travel in a time. And the distance you travel in a time will be affected by the amount of force you're applying. So, like, if you think about a car driving, okay, if you're applying more force, that means that the wheels of the car are turning faster, so it's moving quickly. It's covering more distance in a particular time period, and that's the kind of connection to speed. Speed is equal to distance divided by time. The more force you're applying, the greater that you're going to be moving, okay? Because force is causing that, like we said earlier, you might not have been here at the very start of the lesson. We were talking about the different effects of a force, and a force will either change the shape of an object or change the size of it. It's either going to make a stationary object move, make a moving object speed up, slow down, or it's going to end up changing its direction. So that's what we talk about when force is being linked with speed, is about what effect is it having on its movement, and what that's going to end up changing the distance it covers in a set time. It needs to put a negative sign. Not necessarily. I wouldn't necessarily put a negative sign in there. You could say minus 1,000 newtons to suggest it, but it depends. If you're saying that it's decelerating by 1,000 newtons, then yeah, you could put that in there as well. Can you give an example where the projectile motion has an initial and final velocity equal to 0? I would think, I don't know if this fully answers your question now, because I'm literally just scraping. I'm tired at this stage as well. It's been a long day. Probably like a skydiver reaching terminal velocity. That would probably be a good one, where the force of gravity pulling them down will end up equaling out with the air resistance of them pushing back up against them. So you're going to end up seeing the change in speed is going to be 0. That it's going to be a constant speed instead. Net force is equal to mass times acceleration. Yeah, F equals m times a. Any other question? Is force just another word for gravity? No. So what you're thinking there is, gravity is an example of a force. So a force is anything that's going to basically change something's direction, speed it up, slow it down, all of that jazz. So you're going to end up seeing force being described with arrows, because arrows will show you the direction that that force is acting. Now, if you had an object high up in the air, okay, so that's our object, this is the ground. If you've got an object high up in the air, gravity is pulling it downwards. So gravity is an example of a force. Okay, so that's where we were talking about gravitational being an example of a non-contact force. Can you give an overview of what topic this is about? We were talking about forces, so quick overview of everything we mentioned. We talked about how you would know a force is being applied by to something. So the object would change its shape or size. It's going to change its speed, either slowing down, speeding up, changing direction, all of that kind of stuff. Then we talked about how you apply a force. So we were talking about the fact that you can apply a force by either pushing it, pulling it, or twisting it. They're the kind of 3 examples. You have got 2 groups of forces. You've got contact and non-contact forces. So contact forces are stuff where you physically are touching the surfaces and the force. So stuff like reaction, where you're going to have an object touching another object. They're acting in opposite directions. Tension is where, like, you had a rope pulling something up. Air resistance and friction. And then your non-contact is electrostatic, gravitational, and magnetic. So there, kind of summarise of it. What are we doing? Not a lot at this stage, because I'm going to be finishing up in a minute. Any other question? Can you explain how angles affect the components in a force calculation? I think you're trying to move into kind of pushing in towards vector diagrams. I think that's what you're heading towards. I could be wrong. So I think the basics of what you're asking there is, like, let's say I have an object here, and I've got a force that's pulling it this direction and a force that's pulling it that direction. So what we're going to have is we're going to end up resolving forces here. So to resolve a force and find out where its final resting place is, you need to combine these two, okay? So generally the easiest way of doing it is you find the length of this arrow, you find the angle that it's at, okay? So let's say this is at 90 degrees, okay? So whatever length that is, let's say that's, I don't know, we'll say 10 centimeters, okay? I'm going to take that arrow and I'm going to add it towards the end of this one. Okay, so I'll move it exactly 10 centimeters again. Okay, and again, same angle, it's 90 degrees. So then the object would resolve itself by going from there. Oh, my arrow is shocking, but it's close enough, to there. Okay, so that would be how we would resolve those two. And that's essentially, those two arrows is the same as this. So the object would have moved, if we had these two pulling forces. So imagine we had two people with a rope, each that way, one pulling this way, one pulling up. The object would end up over here from these two people pulling. Okay, that's kind of, I think that's what you're asking about. So in terms of resolving your forces, you just need to find the angles that they're operating at and convert one up. You've got to translate it upwards so that there's only going to end up with one arrow. I think that's what you're kind of asking towards, but I could be wrong.